Alright, hello there. I hope you're doing well. My name is Peyman and I'm recording this video for LEN2002 course. In this video, we are going to do some statistical analysis on wind and solar energy produced in France data. I'll start to load the data, pre-process it, visualize the data to understand it better, and then my friend will build a model and draw the final conclusion from the dataset. So let's dive into the project. Before we start loading the data, we need to install some packages, and I installed them before, so I'll skip this part. And then we need to load those packages in our script. By running this part of the code, I'll load those packages. And let me change this to here. Yes, great. Then we can load our data set using this line of the code. Great. And when we open the data here, as you can see, we have date an hour and we have another date. The first one is redundant, so we're gonna remove it later, no worries. So we have a date, we have a start hour and end hour, and as we can see here, they are all 1 hour intervals that we record the production. Then we have our source, which can be solar or wind, and we have production, which is production in megawatts, and day of the year, day name, and month name, finally. And we can actually we saw our data there, but we can print our first 6 rows of the data here, and we can see the structure of our data sets. And when we print this one, we can see the number of records that we have. As you can see, we have almost 60,000 records. So let's go to the next step and we handle the missing values. As we discussed before, we wanted to remove date and hour because we have another date here, so we can do it with running this part of the code. We drop the column and everything is working perfect. Then we're gonna convert the start hour and end hour to HMS, which is the data type for hours in our programming language. So when we print the structure of our data, and as we can see here, start hour and end hour, they change to HMS, so we can handle it better and continue the process. The next step is exploratory data analysis, EDA. So we can print a brief summary of our columns with summary function, and we can check it out here. The starting date is the first day of 2020 and the last day is June of 2023, almost 4 years. And for example, start hour doesn't matter. If we go to production, as we can see here, the minimum is 0, so some days maybe we didn't produce anything, and maximum we produced 17,220 megawatts, which has a huge gap between third quartile and the maximum value. So something might happen here, as we can see. And day of the year we have 366 days, so first day is the 1 and the maximum is 366. So here we define a function to measure the central tendency and variance, and for the production, because we want it for production. And as we can see here, the mean is 2700 and the median is less than mean. So we can understand that our distribution is probably right skewed because the mean is greater than median, and the standard deviation is 3119. So let's go and start visualizations to understand better. Okay, our first visualization is the, let me see, is the production by year. Let me change it to here. As we can see here, we had growth in production in each year, but the thing we need to consider is that we have the data until June of 2023. So we have growth in energy production in each year, and the midpoint of 2023 is higher than 2022. So we might see another growth in production in 2023, as this chart shows us here. The next one is, let me see, recording hour distribution. As we can see, for example, 5 in the morning or 3 afternoon, we have same amount of recording in each hour. It means we have recorded the data 24/7 and we didn't miss any hour, and this is a good thing in the reliability of our data, as we can see here. For example, imagine we have recorded 5 in the morning more than 8 in the afternoon, 8 at night. So the data was not accurate and we had bias in sampling. But as this chart shows here, we have recorded 24/7 from 2022 to mid 2023. So our data is reliable somehow. I mean, in terms of recording the data, it is reliable. Then we have a pie chart here, which is the distribution of our sources. And as we can see, we have 50% solar energy records and 50% wind energy records, which is another good thing about our data. If we had maybe 9% of wind energy, it was not good, and I mean, we couldn't conclude good things, I mean reliable things from our data. But we have equal solar and equal wind production data. So another good thing about the data, and it makes it more reliable for us and makes the bias less. So let's continue the visualization with this box plot, which is the production by the source. And as we can see here, the median of wind energy produced by wind is way higher than the solar, and the outlier also is way far than the outlier of this one. And this visualization is telling us that the amount of energy we produce by wind is much higher than the solar energy. And if we didn't visualize the last pie chart, I would say, okay, maybe we have bias in our data. but we know that 50% of our data is records about wind and 50% about the solar. So from this box plot we can conclude that we can produce more wind energy. I don't know, maybe it is because we have more infrastructure in extracting energy with wind, or maybe it is easier. But the thing our data is telling us is that the amount of energy with wind is way higher than the amount of energy produced by solar energy. So let's go to the next visualization, which is the distribution of production. And as you can see, most of the days we didn't produce anything and it is zero, and yeah, almost normal here, because maybe it is because wind and solar energy, both of them, they produced on this interval. And when we go far and we produce more energies, we can see the distribution, the count of, for example, the day we produced 10,000 megawatts energy with this solar and wind is less, and it is outlier. And when we go more, it is more rare. So we can understand that we can rely on these parts, on this amount of energy production. But for example, if we want to produce 10,000 megawatts, it is rare, and maybe a wind is more strong in one day, and yeah, it just happened. It is just random, as we can understand from this visualization. And this one is really interesting. This visualization tells us a lot about the data. And this is the average productions by month in those 4 years. And as you can see, we have a sharp decrease when we get closer to the summer. And we have a peak in February, and when the weather gets warmer, it goes down. And in the June, as we can see, we can produce less energy in all those years that we have the data. And this one again is telling us that we can produce more energy in the winter and less energy in the summer.
Hello, my name is Aria, and I will be continuing the project that we did with Peyman. Peyman finished the first half, and I will be continuing the second half. Our project name is the analysis of wind and solar energy production. And yeah, so let's get into it. Let me check where Peyman has left off. I think he finished until normalizing the data. Yeah, I will be explaining the hypothesis testing, goodness of fit test, linear regression model, and ANOVA, and lastly the non-parametric test. Okay, let's start off with the hypothesis testing. So we have two hypothesis tests. Let's highlight the first one, and then we run, and yeah, let me highlight it down here as well to see which part is it. Yeah, so the first hypothesis testing method is the comparison between the mean production in summer versus winter. And the method we use is here, well, to sample t-test. And the data we use is the 2 seasons. These 2 seasons cover up for the summer months. It covers up the months June, July, and August. And for the the winter, for the winter, it covers up the December, January, and February. So as we go down, we will see the T value is negative 35.448, and the DF, which is the degree of freedom, is 22,977. P value is 1, and yeah, so from what we see here, we can conclude that the T value is negative, and which indicates that the mean production in summer is much less than the mean production in winter. I believe in the here, the chart, you can see that the production value in wind energy is much higher compared to the solar one. Let's check it in the months. Wait, actually, let me say this is not the correct one. The correct visuals is, let's check this one. Was it? No, this one. Yeah, here. The visualization number 4. You can see the amount of wind energy production is much higher than the solar one. So as we go down, let me again find the hypothesis. Yeah, here. So let's cover up the hypothesis number 2. Let's run this, and let me highlight here as well. Yeah, this is hypothesis number 2. It compares the variability of wind versus solar energy production, and its method is the F test to compare the two variabilities. The data is the wind data, production values from wind energy, solar data, production values from the solar energy, the results, and the results are here again. The F value is 5.02, the degree of freedoms are those, P value is close to 0, and yeah. So in here the F value is of 5.02, indicating a significant difference in the variances between wind and solar production. So in conclusion, we can say in hypothesis number 1, the analysis, say here, yeah, was number 1. The analysis shows no significant evidence that mean production is higher in summer compared to winter. But in number 2, hypothesis number 2, we say that there is a strong evidence that variance in production differs basically significantly between wind and solar energy sources. Yeah, let's move on to the goodness of fit test. Let's run this again. Let me highlight it here. And yeah, our objective for goodness of fit test is to determine whether the production data follows a normal distribution using the Kolmogorov-Smirnov KS test. I'll shorten it for KS test. So in here in the results, like the data, we the D says NA, p-value says NA. However, the alternative hypothesis says two-sided, which means the distribution of the sample data is different from the normal distribution. We got NAs, but I couldn't figure out why. However, there could be possible issues after I searched about it. One of them was related to the missing values, and the second one was about the number of data being huge and giving an error and not being able to get the correct answers. But yeah, but generally the KS test is a useful tool for assessing the normality of your data, I guess. Okay, let's move on to the linear regression model, highlighting it and then running it. Here, let me again highlight it here. Oops, here. So our objective is to develop a linear regression model to predict this time, to predict an energy production based on the sources of energy. So our sources of energy here are the wind and solar, and yeah, and we also add the day of the year as well in the linear regression model. So linear regression model was created in here with the production as the dependent variable and the source and the day of year as independent variables. Here, production as the dependent, source and the day of the year as the independent ones. Okay, so here we can see the residuals, the mean value, the first quartile, median, third quartile, maximum value, and yeah. So let's, based on the residuals, we can say that the differences between the observed and predicted production values are visible, like here, yeah. And the distribution it suggests that there is a skewness because of here the max value and mean value being like max value being higher and mean value being much lower, negative and positive. Yeah, so in conclusion we can say that the linear regression model indicates that both the energy source and the day of the year significantly affect energy production. And as we can see here again, the wind production is notably higher compared to the baseline category, and production tends to decrease slightly as the year progresses. And that was, as we can see, the regression in, let me find the visualization again. We have the chart here, I think, visualization number 6, I believe. Yeah, here. As you can see, as the year progresses, it's decreasing this one. Yeah. Alright. So yeah, we finished goodness of it as linear regression model, and now we are in the section ANOVA. Let me highlight it and then run it. Yeah. Let's see, summary ANOVA model. Yeah, here. We can, yeah. ANOVA, the analysis of variance. So it is used to determine whether there are statistically significant differences in the mean production between different energy sources. So let's say ANOVA is used to compare the means of two or more groups, and yeah, in this case for us is the different energy sources, the wind and the solar, to see if at least one of the group means is significantly different from the another one. So and yeah, these are the datas here. CDF sum of squares, mean of squares, F value, P values, yeah, significant codes. Okay, I believe that it denotes that the P value is smaller than 0.001, which means it's a high statistical significance. Yeah. And yeah. So in conclusion, we can see that the ANOVA results show a highly significant effect of the energy source on production, with a p-value much less than 0.001, as we say here. Sorry, here. Yeah, p-value. And this means that there is a statistically significant difference in mean production between the different energy sources. Again, for us is the wind versus solar. The large F value here, the large F value and very low P value suggests that the source of energy is a critical factor influencing the production levels. And yeah, let's move on. I believe that's it. Yeah, let's go to the non-parametric test. We run it. Yeah, let me see. Yeah. So, in the non-parametric test, we say that we use the here Wilson signed rank test. It's a non-parametric test that is used to compare two related samples, or to test whether the median of a single sample is different from a hypothesized value. So let's break down the output. In here, the data test, the test is performed on the variable production, and here test is statistics V, and p-value again is less than 2.2, which is essentially 0 when we round it, indicating that it's extremely strong evidence against the null hypothesis, actually. Yeah. And alternative hypothesis, true location is not equal to 0. Okay, this means that the true location is indicating that the median is not equal to 0, actually. Yeah. So overall, I think the results suggest that there is a strong evidence that to conclude that the median production value is not equal to 0. And yeah, this is all about the parts I needed to present. Let's go back and see hypothesis, goodness of test, linear regression, ANOVA, non-parametric test. And yeah, so if you want to make an overall conclusion of all the data, all the analysis, we did the data collection and then data analysis using diagrams and charts. We did normality tests. We did point estimation and confidence intervals. We did hypothesis, and we did goodness of fit test, linear regression model, ANOVA, and application of non-parametric tests. Yeah, so we could say in conclusion, this, I believe, comprehensive report covers the various aspects of data analysis, from initial data inspection to the advanced statistical testing, providing I guess a good understanding of what the data is and the data set and their implications in energy production analysis. Yes. And yeah.